Right, so we're going to start looking at optical phenomena and take you through some of the issues. Before you understand optical phenomena, the important thing is we need to understand how radiation coming from the sun, most of it is ultraviolet, but any light that comes from the sun interacts with the atmosphere. Now, it's a well-known fact that the atmosphere absorbs a lot of the radiation that comes from the sun. That's why, for example, the hole in the ozone layer is such a problem, because the hole in the ozone layer doesn't absorb enough radiation, and therefore we get seriously sunburned. So the atmosphere has a protection role. It protects us from the radiation, and different layers in the atmosphere absorb different frequencies of radiation that are coming through. And we need to understand a little bit how this works. So much of the radiation that comes through is in the ultraviolet range. It is absorbed by molecules suspended in the atmosphere. We've got oxygen, we've got ozone, we've got a number of other molecules in the atmosphere which absorb the radiation that's coming through. When the molecules absorb this radiation, when the molecules absorb this radiation, they then radiate the energy back out as heat, and we'll have a look at exactly how that happens. But the net effect is that this process of radiation being absorbed by the atmosphere has a net warming effect on the Earth. And we'll go and have a look now how that actually works. So assume this is a little gas molecule that is absorbed, that is suspended in the atmosphere, and there is radiation coming from the sun that is incident on this molecule. What actually happens is the molecule can vibrate. This radiation can cause the molecule to vibrate. And as the radiation causes the molecule to vibrate, the radiation is then absorbed by this molecule. Now, the vibrations, I mean, I've just illustrated it here with a very simple little animation, but that can be very complex. The molecule can vibrate in a number of different ways. We don't need to go into all of those. We don't need to understand them. It's enough to know just that the molecule can vibrate, and in so doing, it absorbs the radiation that is actually incident on it. Now, as the vibration takes place, you know that vibrations and increased vibration of molecules is the measure, is what we call heat. It then radiates that energy out by vibrating through friction. It can then cause heat to be emitted in the atmosphere. So effectively, this radiation is absorbed by the molecule vibrating, and then that is radiated out again as heat. And you can see some of that heat goes back up to the atmosphere, but some of it actually comes down towards the Earth. So I've put it here in words. This light is incident on the molecule, causes the molecule to vibrate in a number of ways. When this occurs, the energy is therefore transferred to the molecule, and then it becomes heat. So it's transferred to the atmosphere, and the atmosphere warms. The light is effectively therefore being absorbed by the molecule, and the increased vibrations is evident as increased temperature of the gas. So the gases in the atmosphere are therefore effective in absorbing the energy from the sun, and that contributes to global warming. And you can see how the gas molecules would therefore heat up the atmosphere around them. Now, how does this happen with a metal? Well, that was a gas molecule, all right? Well, any atom that has light energy incident on it, light energy that is striking it, and particularly in metals, what can happen is, because metal electrons are not strongly held, when light energy strikes the atom, the electron can be excited up to higher energy levels. And that in so doing, the incident light would then be absorbed. Now, what in fact happens with metals is those higher energy levels are not stable, and so the electron will drop back down to a lower energy level, and that will again radiate out the same frequency of light that was absorbed. And so that's why metal surfaces are shiny, because they're radiating out energy that they have absorbed. And here we've got it in words. So the light incident on metal atoms can excite the electrons up to higher levels. That absorbs the energy, and the electrons can then drop back down again and radiate the light out. So this gives the metals their shiny luster or shiny surface. Electrons absorb the light, go up to higher energy levels, and drop back down, and that energy is then radiated out. So that's how metals can get their shiny surface. But we see what we are looking at here is the interaction between substances and light. And in most cases, most substances are able to absorb some energy from the light. Now, that leads us on to consideration of spectra. Now, there's three main spectra that the syllabus covers and you need to know about. So in the middle here, this first one, if we take light from an incandescent bulb, which just heats up and gives off nice white light, and you put it through a spectrum, through a prism, you know that the light is refracted by the prism and different colors are refracted different directions. And so if you look at that light, you will see a continuous spectrum and you'll see all the colors of a rainbow. And that we are familiar with. We do that in many different, that's been seen many times. Now, if you, instead of using the light from an incandescent bulb, if you take a gas that is being energized somehow, now here it says hot gas, you can use a hot gas or you can actually use an energized gas. You can energize the gas by using electricity. The gas can begin to, if you put enough energy into it, enough heat or enough electrical energy, the gas can begin to glow. If you take that light and put it through a prism, then you see a very different kind of spectrum. You do see a range of colors, but they aren't continuous like this. You see specific lines. And that is called a line emission spectrum. And it's produced because the atoms in the gas get hot. The electrons are again jumping to different levels. And as they fall back down, they radiate specific frequencies. This turns out to be very useful because if you change the gas, you get a different set of lines and they're spaced differently. And there'll be different colors. And it turns out to be something of a fingerprint for that gas. You can use that spectrum to identify every gas. Every gas would have its own unique spectrum. This, I think, is supposed to represent the hydrogen spectrum. I'm not sure how accurate it is. Now, another interesting phenomenon, if you take that same gas, but instead of energizing it and making it hot, you instead shine the light from an incandescent bulb through that gas. And then take the light that emerges from the gas and put it through a prism. And what you now see is a strange combination of these two spectra, where you'll get the continuous spectrum, but with the lines from the line emission spectrum missing. The exact same frequencies, but they will not be there. They'll be missing. And the reason that they're missing is that the frequencies that are emitted by a gas when it's hot are the same frequencies that that gas will absorb if it's cold. And so that we call an absorption line spectrum. And this, again, would be the specific lines corresponding to that gas's fingerprint, if you like. So here we've put it into words. Light passing through a prism forms a continuous spectrum. And that gas, if it's energized, it can emit light. So that's this example here, which will give you the line emission spectrum. And then if that same light is shone through a cold gas, then we'll get the line absorption spectrum. And so the syllabus expects you to know the difference between those two and to be able to explain them. Right, so we'll move on. So let's just consider for a minute, how does the absorption spectrum appear? You have energy that's incident on the light. It can be light energy, it can be ultraviolet light, it can be electrical. That energy can be absorbed by the atom as the electrons jump to higher energy levels. And that is how the absorption spectrum can occur. So there it is in pictures, electrons going up to higher levels, and there we go in words. Radiation is absorbed by electrons being excited to high levels. How is the emission spectrum produced? Well, you can have all different types of energy given to atoms. It can be electrical, can be heat, could be light energy. As we said, that energy hits the atom, the electron absorbs the energy, goes up to a higher level. However, the higher levels are unstable. So that was the absorption part of it. Now, because it's unstable, that electron may fall down back to its original ground state. When it does so, it will lose energy. And that will give you your emission spectrum. So the emission spectrum is produced by radiation, which is being emitted by electrons falling back down to lower levels. Right. Now, this can be seen here. We should look at it in a little bit more detail. These, in this picture, these levels E1, E2, E3 stand for the various electron energy levels that are available in an atom. Now, whatever atom it is, this would be the ground state level. The nucleus would be down here somewhere. And this would be the first electron level, so the 1s level, that might be the 2s level. And these are all different energy levels available to electrons in an atom. Now, we've said we can excite electrons up to various levels by energizing the atom. And when they are up there, it's unstable. And if there's space gaps below them, they will then fall back down. Now, the gaps in these electron levels, the gaps of energy gaps between the different levels, turns out that they correspond very nicely to different colors of light. The energy of light is associated with its color because it comes from the frequency of the light. And so in this atom, for example, let's say a transition, an electron falling from E2, the second energy level that's available, down to E1 would result in red light. But if it fell from E3 to E2, it would result in yellow light. And you can see, because an atom has specific energy levels, which are determined about how many electrons it's got and how many protons, crucially, each atom from a different element would have a different set of energy levels. The energy levels might be closer together because there's more protons and they pull them in closer, or they might be slightly further away, which means the energy gaps in each atom would be unique to that atom, which means the colors associated with electron transitions in that atom would also be unique to that element. And that is why we get a unique line emission spectrum or absorption spectrum from each different element, because they've got different gaps in their electrons, in the energy available to the electrons. So that's in words, and here we've got it, that's in pictures, and here we've got it in words. Electrons dropping from higher energy levels radiate energy. The frequency or the color of the energy radiation is directly related to the gaps in energy, because each element has specific series of energy levels. They therefore have specific absorption lines. And the line spectrum can then be used to identify an element. It can be the fingerprint of each element. Right, so that completes our initial discussion of the various types and ways that energy can be absorbed by atoms. And that'll be enough for an introduction to this section of optical phenomena. And our next section, we'll move on to consider the photoelectric effect. So we will come to an end here.